And thank you very much for giving me this opportunity to have a presentation at this. Hello, can you hear me? Okay. Thank you very much. And I'm Ryuichi Kanai from University College London, a PhD student working with Serge Giros. And today I would like to introduce functional history matching method, which is a new method we are developing. And our research, our study is combining simulation and data science. And as you know, when you run your simulation, you would have many problems. For example, it's very difficult to know what is appropriate input parameter values in advance. And also, you know, all models are, in a sense, wrong. So it's impossible to have a perfect model. So your model can have model discrepancy. And also any kind of a computation, simulation has computational cost, expensive computational cost. And to solve these problems are very difficult. And in our study, we focus on input parameter values. And solving this problem, we use data science method, for example, Gaussian process regulation, and so on. And mainly in this presentation, I would like to introduce our method, functional history matching. But now, what kind of simulation? in our research, I use tsunami simulation because I'm from Japan. And you know, in Japan, we often experience huge tsunami. These photos are tsunami case in 2011. And at that time, I was in Japan, and the tsunami caused terrible, terrible situation. And the problem was many people couldn't evacuate at this time. The reason was the Japanese government misestimated the tsunami height even after the earthquake occurrence. Japanese government had a cutting-edge technology about tsunami simulation at that time. However, it was extremely difficult to estimate the tsunami height even after the earthquake occurrence. The problem was they used wrong input data for your simulation. So like this, estimating input parameter values for tsunami simulation is difficult and it's demanding. So we would like to solve this problem using the data science method. Now, firstly, you know, in the case of the tsunami simulation, it's necessary to input the location and the shape of the initial tsunami. And about the location, location means the tsunami source location, so latitude and longitude. I use the Gaussian process regression. And the main part is the shape of the initial tsunami, height, major axis, minor axis, and angles. To solve these problems, functional history matching can be applied. Now, firstly, we focused on a physical mechanism. When an earthquake occurs in the ocean, it causes tsunami, and the tsunami causes uplift sea surface change, like this one. Then the air above this tsunami is pressed by this uplift sea surface change, and as a result, air pressure, acoustic waves, propagate from sea surface to the space. In the end, this air pressure causes disturbance in the ionosphere, specifically electron density depression. Fortunately, this depression can be captured by GPS satellites, but there are problems. As you know, GPS satellites are moving, therefore observation points are also moving. And also GPS satellites are not uniformly distributed, so observation points are not uniformly distributed. And the number of GPS satellites are limited. Therefore, even if you have observation data, the red star mark is the location of the epicenter. Even if you have the observation data, you can say something. Oh, there is disturbance, depression near the epicenter, but it's impossible to say about location of the tsunami source. So then we used Gaussian process regression. Of course, it's necessary. Whenever you have your observed data, it's necessary to exclude noise and outliers. To do so, we use very basic techniques, so the moving average or MCMC, sequential Monte Carlo, or particle filter, particle MCMC, and also based on nearest neighbor, k-nearest neighbor method, we excluded noise and outliers. And after that, we applied Gaussian process regression for the observed data. But there was a problem. As you know, when you use Gaussian process regression, the computational cost is order of n cubic if you have n data points. So it's computationally expensive. However, what I want to do is create a warning system for tsunami case. So it's necessary to process data in real time. So n cubic is too expensive. So to reduce the computational cost, we applied INLA SPD method, integrated nested Laplace approximation stochastic partial differential equation method. So strictly speaking, the solution of the specific type of stochastic partial differential equation is Gaussian field, but we introduced an approximation, the Markovian property. So the solution is Gaussian Markov random field. And this solution can express the fitting surface. Of course, to accelerate it much more, we use the parallelization. But important thing is, compared to the ordinary Kolesky decomposition, the computational cost is order of n cubic. This approach is much easier. I mean, the computational cost is order of n to 3/2, so it's much faster. As a result, our computation can be completed less than a minute. And applying this technique from the original data captured by GPS satellite, we can have this fitting surface by Gaussian processing. The fitting surface is expressed by red surface. And after getting this surface, we projected the surface onto 2 dimensions. Here, you can see this disturbance, depression, is caused, but it's not the same location with its epicenter. So it means tsunami location is different from the epicenter. And using this estimated depression disturbance, we can estimate input data about the location. So we used weighted average of the depression. Weighted average point is expressed by this black triangle, and this contour is true initial tsunami data. So using satellite data and Gaussian process regression, we can estimate tsunami source location latitude and longitude by weighted average of the estimated depression. So using data science method, it's possible to estimate input parameter in the case of the tsunami about location. But the problem is the shape, height, and so on. But to solve this, I would like to use a method called history matching. Now, what is a history matching? And this is a rough concept of the history matching method. History matching method is used to estimate plausible parameter subspace, plausible input parameter subspace. If you have a simulation and you don't know an appropriate input parameter values in advance, you would like to have plausible parameter subspace. Then all you need to do is just pick up input parameter values from your plausible parameter subspace. But how can you define its implausibility or plausibility? The history matching method can provide answer to this question. This is rough explanation and using one-dimensional experiment. You have observation data at minus 0.8 here, and you have your own simulation model, F simulation, and then you run your simulation 6 times because it's computationally expensive, so you don't want to run simulation 7 times or 8 times, but it's not sufficient. After running your simulation 6 times, you would like to create an emulator using this 6 simulation output. In this toy example, I use Gaussian process with Met and Kanai, and you can have emulation output with its uncertainty. And implausibility in history matching is defined by this formula. The numerator is the distance between observation data and mean value of your emulation output. So this implausibility is roughly the distance between your emulation output and observation divided by its uncertainty. Using this implausibility definition, you can calculate implausibility. This is the implausibility. And you can set a threshold in this case, the threshold is 3. And if your output implausibility is less than 3, then you can say this region is plausible. And you can have plausible parameter subspace. You can repeat this procedure several times. For example, you can choose an additional data point from this plausible parameter subspace and run your simulation one more time, and then you can again create your emulator based on 7 simulation output. But in this time, uncertainty becomes smaller because you have your additional data point, and the implausibility shape is changed. And finally, your plausible subspace shrinks. Then you can choose your plausible input parameter values from this plausible parameter subspace. This is a concept of history matching. So what we want to do is we want to have a plausible parameter subspace. But yeah, we have tsunami simulation data, tsunami data. So it's not discrete data. Tsunami shape is a surface. Even if you fix longitude or latitude, it's a curve. So it's not a discrete data. So it's necessary to expand the method from discrete to continuous one. Imagine that this is just a toy example. You have observation data expressed by black curve. And the physically nearest curve is green one, but the shape is totally different. You want to pick up blue curve based on your own method, but it's difficult to define the distance between curves. And I don't have sufficient time. So yeah, let's skip the, LP norm might work, I thought, but it didn't. When you use L1 norm, L2 norm, L infinity norm, the result is green curve. It is the nearest one. And if you project your curves onto RKHS, reproducing Kanai-Hilbert space, and compare each curve using its coefficient, but even if you use coefficient, the result is the green curve is the nearest one. Similarly, I use the functional principal component analysis and using its score to compare each curves, but the blue curve is not selected. And there are many other metrics or methods to compare curve similarities, but in many cases, it doesn't work because many metrics do not consider about its shape. To consider its shape, it's necessary to differentiate curves. And the solution can be Sobolev norm. In the Sobolev norm definition, you use the differentiated curves. And in this toy example, if you differentiate the original curves twice or 3 times, the blue curve is selected. So we think that this Sobolev norm can be used for the definition of the implausibility in functional data. And using this definition, we would like to show that the technique can work very well. This is a emulator, functional emulator. Using this emulator, it's possible to compute the Sobolev norm. And this is the Sobolev norm of emulator output. And you can see that this area is smaller than our area. It means this input parameter combination, θ1 and θ2, provide a smaller Sobolev norm. And using this Sobolev norm, we can compute implausibility and set a threshold and choose input parameters less than threshold. And using this technique, this is just a toy synthetic data toy example, but you have 20,000 emulation outputs. Not all curves look similar to the true data, red curve, but choosing plausible input parameter using Sobolev norm implausibility, you can have these curves, and these results look similar to the true curves. So we believe that our new method for functional data, functional history matching, can work. And as a future work, I would like to apply this technique to tsunami simulation. There are many open source tsunami simulations, and this is one of them called Jaguars. And we would like to apply our method to this tsunami simulation to create tsunami warning system. And to sum up, data science method can be useful to estimate input parameter values for simulation. And in our method, we use Gaussian process regression and functional history match. Thank you very much for listening.
Thank you. Any questions?
So your method for this implausibility measure reminds me of kind of Bayesian optimization and with similar objectives. But I guess there the hyperparameters of the Gaussian process are going to affect even more basically what's your kind of plausibility subspace. So do you optimize those parameters or do you pick them arbitrarily? So how do you handle the hyperparameters for this?
Yeah, in this case, I optimize the hyperparameter using the input, in this case, 7 input or 6 input parameters. And also, it affects, I mean, the kernel itself can affect its emulator. For example, I use Matan kernel, 3/2 Matan kernel, but if you use, for example, squared exponential, the emulation output would change. As a result, implausibility value also change. So as you mentioned, it depends on emulator, how to create emulator. And it means hyperparameter of the Gaussian process or the kernel selection can affect. So there is no only one answer. So if you use another hyperparameter combination, or if you use different kernel, the result would change. But even in such a case, you can have plausible parameter subspace, and it can be validated. Not even though the result is not the same. Am I answering?
Sure. Yeah.
Yeah.
Any final quick question? Okay, I think just for time reasons, we'll probably move on. Thank you very much, Ryuichi.
Yeah.